In this video, we are going to complete the proof of the proposition that we started last class. Remember, it has two parts. We already proved the first part in a previous video. The second part says that given three distinct points in the Riemann sphere in the extended complex plane, Z1, Z2, and Z3, and three images, W1, W2, W3, also in the Riemann sphere, this means this could potentially be points of infinity. Okay, one of them could be infinity. Then there exists a unique Mobius transformation such that the images of the Zj are the Wj, and here the order is important. Okay, so Z1 gets mapped to W1, Z2 to W2, and Z3 to W3. And the transformation W equal T of Z is given implicitly by these ratios, okay, W minus W1, etc. This is implicit because you need to solve for W here, but you see there is W in the numerator and denominator, so it requires a bit of computation. This is not the easiest way. This is interesting from a theoretical point of view, okay? But this is not the easiest way to go when you need an explicit expression. We'll see more about this. Before we continue, let me make a remark here. This proof contains an important algorithm. Okay, what happened there? An important algorithm to find Mobius transformations explicitly. Okay, so it's a proof worth going through. So let's see how the proof goes. It's actually fairly straightforward. Now, the key idea in this proof is to not try to do the full generality all at once. Okay, instead of mapping Z1 to W1, Z2 to W2, Z3 to W3, let's start with a particular case. Okay, and the particular case we want to know is when we map Z1 to 0, Z2 to 1, and Z3 to infinity. Okay, these 3 points are very important. They are very important because they behave in a very special way. And for these 3, we can guess what the transformation is. Okay, so we always go first with the point of 0. Okay, that's the first one to go. And here what we need to realize is, okay, there are going to be 2 fractions here. So if I want, let me jump this so that we don't have that line bothering us. If I want to have a 0 at Z1, I want definitely a term like this, Z minus Z1. Okay, you see? This goes first. Now, the second we want to deal with is the point of infinity. The point of infinity, let's do orange. Oops. Okay, so the point of infinity goes where? Let's use blue. So when we want to send something to infinity, then we need to make sure we divide by 0. Okay, that's the way to end up in infinity is dividing by 0. Ask a computer, they will tell you right away. So then z minus z3 has to go in the denominator. Whoa. Okay, so this is the second thing we write. And then the third and last. Okay, and let's use green. The third and last is just an adjustment to make sure that when we evaluate z2, we get 1. Now, see how things look now. If I evaluate z1 here and here, this is not 0, so it's okay. But this one here gives you a 0, so this one check. Now, if I evaluate infinity over, whoops, sorry. If I evaluate z3, okay, this is fine. This is non-zero, but this produces a division by 0, so we get infinity. So this one also okay. Now, if I evaluate z2, this is some number, but it's definitely not 1. So I need to adjust here for what is missing. So I adjust z2 minus z3, z2 minus z1, just cross products. Okay, and this is the third step. And this is the algorithm I was talking about. Okay, with this idea, you can find any example you want of a mapping that maps any 3 points, z1, z2, z3 to 0, 1, and infinity. Okay. Here, just a warning with appropriate interpretations. If some of the, not some, if one of the CJ is infinity, okay, for some J. So in that case, we need to adapt a little bit the formula. For example, if Z2 is infinity, okay, what happens if Z2 is infinity? Well, when we look at this term, right, we are saying infinity over infinity, but we agreed in complex analysis, this is a calculus one student dream. You can just kind of simplify and say, well, you know, this is 1. All right, so then we get T of Z equals Z minus Z1 over Z minus Z3. Okay, that's just a small detail that can throw you off if you haven't thought about it beforehand. Okay, now this doesn't really answer the question because we wanted to map Z1, Z2, and Z3 to W1, W2, W3. Doesn't quite, but actually does. How come? Well, remember the set of Mobius transformations, it is a group. So we don't need to do all at once. We can do in 2 steps. We can generate the mapping by finding 2 mappings. Okay, we can map Z1, Z2, Z3 by some mapping T to 0, 1, infinity, and we can map W1, W2, W3 to 0, 1, infinity using some other map S. Okay, we will find them the same way. Now, the key point is that if you want to skip over and just want to go from the Z's to the W's, then the mapping you want to use is T composed with the inverse of S. Okay, so you just go first to 0, then to W1 by taking the inverse. Okay, now here, notice we have T of Z, which is Z2. I'm going to go ahead and just copy the formula instead of just spending time writing it. Okay. And then you have S of W, which is W2 minus W3 divided by W2 minus W1 W minus W1, W minus W3. Okay, and this gives us the implicit formula that we were talking about. Okay, because they are going to map the Z's into Z, 0, 1, infinity, and the W's, then we get, let's put this one first, equals the other ones. Okay, so done. This is the implicit formula for W equal T of Z. But if we want something more explicit, I'm realizing, let's just call this R. Okay, so that we can say that this T is S minus 1 R. Okay, sorry about that. There we go. So this is the implicit formula for T of Z. But if we want something more explicit, we can still compute it. Okay, to compute something more explicit, remember that T of Z is AZ plus B divided by CZ plus D, right? So that's a matrix A, B, C, D. Again, R. This is S of Z is going to be alpha Z plus beta over gamma Z plus delta. That's associated to alpha beta gamma delta, right? So I have the R and I have the S, and now I just need to find T is first apply R, then S minus 1. So that's associated with the inverse, the product of the inverse times the ABCD matrix that gives me R, okay? The inverse is always very easy. You just change the elements in the main diagonal and change the signs on the anti-diagonal. And you don't have to worry about dividing by the determinant, because multiplying by a number doesn't change the transformation. Okay, so this is very straightforward. You can compute it. Compute the coefficients. And you have the explicit formula for T. Okay, and this is almost every time much easier than actually trying to solve from the implicit form. Okay, the implicit form has its interest also. Sometimes you can just go ahead and use it to write a transformation. So now, how do we show that this is the only possibility for such a mapping? So let's say we have two mappings, T and S, that map Z1, Z2, Z3 to W1, W2, W3 in that order. Okay. Now, if we take the composition of T and S minus 1, we can say here instead, then this composition, what is it going to do to each of the ZJs? So you see, this goes S minus 1, T of ZJ, which is WJ. So this is S minus 1 WJ And let's see now. So S is going to send Zj to Wj. So the inverse sends Wj to Zj. So this is Zj. So see what happens. We have a mapping here that fixes the point Zj, but Zj can be 1, 2, or 3. So the composition of T and the inverse of S fixes 3 points. Okay, and in the previous video, the previous proposition, we saw that there were only 3 possibilities, either fixes 1 point, 2 points, or all the points. So S minus 1, the composition of T and S minus 1 fixes all the points. That only happens when it is the identity. Okay. Therefore, T and S must be the same.